Alright, so continuing. Um, so coordinate change in Fn is even nicer. If we have a basis, again using v1 through vn for the one basis, v bar 1 through vn for the other basis of this time column vectors, well, in this context, when we can just concatenate the basis to form an n-to-n matrix over F. And also, when we look at the basis expansion, we can rewrite it in terms of a matrix column multiplication. So this formula is so precious, just the vector is equal to the basis matrix times the coordinate vector. This is, only you can do this for column vectors, right? But if you can do it once, you can do it twice. And so then these are just two different ways to build X, one from the beta basis, one from the beta bar basis. And so we have this equality, and then we can solve for the basis, the coordinate vector with respect to the beta bar basis, and there it is. So the coordinate vector with respect to the beta bar basis is we multiply by the inverse of the beta bar matrix times the beta matrix times the coordinate of X with respect to the beta matrix, and that's how you change coordinates on Fn, or usually Rn. There's even a more special case. Well, by the way, the coordinate change, the change of basis matrix is in this case this guy. And there's an even more special case if beta is the standard basis and beta bar is the non-standard basis. Well, that case, the beta matrix is just the identity, and so these formulas simplify even further. To calculate the beta bar coordinates, we just take beta bar inverse times x, and the change of basis matrix is just the inverse of the basis matrix for the non-standard coordinate basis. So that's pretty simple. Now, I have I think a reasonably decent example in the notes, which I'll talk through here at this point. Two-dimensional case, right? So here I have, so think of gamma as equaling beta bar for the purpose of this discussion, all right? And so I go from the 1, 1, 1, 1 minus 1 basis to the 1, 0, 1, 1 basis for R2, and I calculate the coordinate vector of v with respect to the base, with respect to beta and gamma for a specific vector, 2, 4. All right, so I'm looking for the coordinate vector with respect to beta and gamma. Here's my basis for beta, my basis matrix for gamma. We can calculate the inverse using the 2 by 2 formula. Multiply by the inverse for the 2 by 2 times the given vector. That gives us the coordinate vector of v in the beta basis. Here's the coordinate vector of v in the gamma basis. Simple as that. And so, continuing. So what do we got? Let's see here. So then I actually then just calculate the change of basis matrix from going from beta to gamma coordinates, like so, right? It's supposed to be such that when I multiply that matrix times v beta, I get to v gamma, right? The coordinate vector for v with respect to gamma. Is that the case? Well, here's the change of basis matrix, allegedly. Gamma inverse times beta works out to that. And then if we take that alleged change of basis matrix, 0, 2, 1, minus 1, and multiply by 3 minus 1, which was my coordinate vector of v in the beta basis, change basis, change coordinates rather to gamma, I get minus 2, 4, which is, of course, what I calculated independently in that way. And just to try to bring things together here, what's really going on is that, there's geometrically, there's this one vector, right? That's 2, 4. And the point is that we can build it using the gamma basis, or we can build it using the beta basis. I'll do the gamma basis in blue here. So the gamma basis, it requires what? It requires that we take, minus 2 copies of, let's see here, minus 2 copies of the first one, and 4 copies of the second one. So the minus 2 copies, this is the minus F1, and then it's supposed to be, let's see here, minus 2, wait a minute, oh sorry, that's the beta basis. I'm doing the beta first. 3 copies of the first thing in the beta basis minus 1 copy of the second thing, right? And then with respect to the gamma basis, if I could just keep my example straight, that'd be great. With respect to the gamma basis, we need minus 2 copies of the first thing in the gamma basis, and then 4 copies of the thing in the... What? Oh, I'm an idiot. This is not a comparison between the gamma and the beta basis. What is this? This right here, of course, is how you build V with respect to the standard basis. I gave up on trying to draw beta and gamma in the same picture. Oh, sorry, I was a victim of my own notes. Anyway, it's also interesting, of course, to just contrast the coordinate formulas. So like the coordinate formulas, if we take V being xy, then the beta coordinates of xy, 1/2 x plus y, 1/2 x minus y. On the other hand, if we were to use bars to denote those, then we'd have x bars 1/2 x plus y and 1/2 x minus y. This is the relation between the beta coordinates and the standard Cartesian coordinates x and y. And you can invert them and get that as well. It is unfortunate that the bars here do not have any relation to beta bar being gamma in this context. My apologies. It's just a quirk of this current conversation we're having. All right, so that's that. I hope that gets you started on coordinate change over column vectors. I'm going to pick up again here with how to coordinate change for abstract linear transformations next, guys. Thanks.